Hey everybody, Dave Lindberg with another episode of THD Podcast. Today we have Geoff Hill joining us from the UK to talk about his measurement. I'm going to call them boxes. I don't think he likes that word. He's going to teach us all about what makes that different.
Enclosure.
They're like mini anechoic chambers in my rudimentary understanding of audio engineering. But before we get into that, let's remind everybody to check out our sponsor, the ALTI, the Audio Loudspeaker Technology International. Please hook up with Barry and find out about all the benefits of networking with his organization. They do have an event coming up in Orlando, October 24th, 25th. So check in on that and see if it's something that will help your business. All right. So here we are again. Simon joining from Japan. How's it going today, Simon?
Very good. Good evening. Good morning.
All right. And Geoff Hill from his setup in the UK with his brand new microphone.
Yeah, we had a bit of noise last week, so I've got a cardioid microphone which should reject any noise, but of course the neighbours aren't making any noise today.
Okay, all right. So everybody watching, we're recording on a Sunday, so that might help with the construction noise in the office here in an industrial building, and perhaps the neighbors renovating in the UK. So. All right. Well, let's get into this. So yeah, this was kind of arranged by Mike Klasko. He connected us a while ago, and it took us a while to get on here, but we're on here today. So, like I said from the intro, that it's everybody who's worked in acoustics has at some point stepped into these funny rooms, and you close the door and you can't hear yourself clap, and these kind of funky things. And it's meant to be an isolation room to do audio measurement. Now, you've got something that can perhaps make that portable or more flexible in speaker production, in speaker testing. So maybe give us a preface of a little bit of your background, and then tell us about these test systems that you, test chambers, let's call them, that you built.
Exactly. Test chambers is the way that I prefer to think of them. I've been and was a loudspeaker designer for many, many years. And one of the things about designing loudspeakers is inevitably you need to measure it. You need to measure it to confirm that the design that you've thought of and worked on is, first of all, working as you intend it to work correctly. And then secondly, once you've got the first initial prototypes built, you've then got to measure them in production and ensure that the production is stable, and that the first one that you make is the same as the 100,000th or the millionth or 10 millionth. And the default way in the industry of measuring them is the anechoic chamber. Well, anechoic chambers, in case people didn't know, were originally a general purpose design developed by the military in the midst of the Second World War, primarily to characterize loud noise sources and also to measure military vehicles in the run-up to D-Day and the invasion of Europe. And they're designed to handle large objects and be general-purpose tools. And the greatest general-purpose tools, but as general purpose and measuring loudspeakers like a typical 4-inch or 5-inch speaker is not the same. You need, for production and for ongoing QC or development work, you need to do exactly the same measurement every damn time. And if you don't, you inevitably get variations. And then you're forever chasing down, well, is the measurement right? Is it set up correctly? Has it been connected correctly? And worst of all, is the environment affecting it? And anechoic chambers being large and bulky and expensive are rare on the ground, and they tend to get filled up with, pardon my expression, crap. Because people say, well, this is an enormous great thing. It doesn't seem to be doing much for anything most of the time. So they tend to get filled up with junk, and they say, well, we can use this corner or that corner, and there's a bit of stuff there. So we'll move the measurement around from there over to there. You end up in all sorts of messes. And so it's just not a good situation. And throughout my career, I've had to put together measurement systems for various companies. And when I, around about 10 years ago, became independent, one of the things that I was trying to do was to work out where to go. And it came up that another company came to me and said, we need a measurement system. Great. Of course, they didn't have sufficient money for an anechoic chamber. Neither did they really want one. They didn't need one, but they did need something that would do the job. And that's how the impetus for the TTC, a Tetrahedral Test Chamber, came about. So that's a bit about my background and where the idea came from.
And the tetrahedral, remind us how many sides to a tetrahedron? Is that what it comes from? Tetrahedron?
Tetrahedron, exactly. Okay. It's one of the platonic solids, and it's the only platonic solid that's got named after Plato. That's got 4 sides. The pure tetrahedron is constructed out of 4 equilateral triangles.
Okay.
And that's not terribly practical for a loudspeaker test chamber. And so I've used a form which is, I forget the exact name of it, but basically it's based on right angle triangles. There is a full name, but I can't remember it, which is based around the right angle triangle rather than the equilateral triangle, which makes it a more practical concept.
Okay.
So it's inherently a strong, robust structure with many other advantages as well.
Okay.
So is it that the measurement chamber is trying to replicate the effect of an anechoic room?
Both yes and no. An anechoic room has certain advantages, and one of the things that is designed to do is to absorb all the sound waves equally at all frequencies. The problem is that low frequencies, none of them, and I do mean none of them, can actually do that. The reason being because of the wavelength of sound, which is 345 meters per second, which means that at 1 kilohertz, you've got a wavelength of about 0.34 of a meter. So half wavelength where you get absorption is about 170 millimeters. That's easy to absorb, no problem. But take the other end of the spectrum and we go down to even just 100 hertz. Now we've got a wavelength of 3.4 meters. And 3.4 meters, half the wavelength of that is around about 1.7 meters. You can just about practically build wedges which are 1.7 meters long, just. But you're pushing it even at that point. You know, you're talking nearly 6 feet long. Much longer than that, you just can't do it. You just cannot absorb those sort of frequencies, yet alone if you go below 100 hertz. And most speakers are required to work down to somewhere in the region 20 hertz, 30 hertz, 40 hertz, at which point the wavelengths, if you were to take 10 hertz, you've got a 34 meter wavelength. 17 meter wedges, I've never seen any chambers in the world with 17-meter wedges.
The wedges on the side of an anechoic chamber being half the wavelength. Where's that half wavelength come from? Is that sort of a general guideline for the?
It's a general guideline for absorption. In order to absorb rather than resonate a wavelength, because the wavelength sine wave shape comes up and down, the half wavelength is the point where it comes up to there and then back down to the zero. And it's at that wavelength, a wedge that is that long is capable of fully absorbing the sound. Any shorter than that, and you will get destructive interference and not as good a absorption. Okay. It's just and that goes for sound, it goes for light, it goes for all wavelengths. If you're going to absorb it, you've got to be at least that length in order to be able to do it. There are other tricks you can do, but they work with different physics. So that becomes a hard, fast rule that virtually any practical anechoic chamber can't measure lower than around about 100 hertz. Even the biggest ones, they may be very, very quiet and get noise levels right down to zero, which may or may not be of importance. I would argue that it's of less importance than many of the other things. And so that becomes a hard and fast rule that most chambers can't measure much lower than that. One way of doing it is in a fully reverberant chamber, which can measure lower because you're not trying to absorb it. Great. So in the TTC, we take the point that at low frequencies we can't absorb it. We know we can't absorb it. Don't even try.
Okay.
Instead, we absorb the higher frequencies, which we know that we can absorb effectively, and then we deal with the low frequencies via equalization, which with modern test equipment is perfectly easy to do. I can perhaps share with you a graph at this point, which may indicate what's going on better. So bear with me a moment.
Perhaps if you also have an image of what we're talking about, because we haven't shown people conceptually what it is. So let's maybe have a look at one and then go to the chart to see what the results are.
Okay, all right. Okay, now this is a TTC 350, and I'm putting a baffle on it, as you would have for virtually any loudspeaker measurement. You make those up for every driver. Standard clamp that we put on there in order to measure it. We get our connections. Positive, negative, and away we go. We take our connection and we plug it in the back. Nothing untoward there. Now, if I do it from scratch, I will call that the int 350 internal response. We'll do another measurement, which we're just doing it near field. Now we can see there we're nice and clean and response. And that the response of any drive unit in a closed box is just straight 12 dB rise. That's what they do. That's what theory says it does. So that's what it does. I'm just going to put a tiny little bit of smoothing on there just to get rid of the noise. And that's all. And then we'll say, okay, next, 50. Sorry. I just divide the two. That gives me the rough EQ.
So actually, this red curve is that is a microphone on the outside of the chamber.
Yep, on the outside of the drive unit.
It's like taking a reference.
Yep. And this is only got to be done once. I've been playing around with different setups and different instruments and everything else, so someone's got a bit confused. So we just go from scratch. If I change back to the screen, is the camera gone? Oh, don't worry about it. Not EQ. All thumbs today. Sorry. Zero. Now all I've done is I've just put that to zero. Q350. Now, if I take my measurement that I did earlier, which is the internal measurement, and I take the one that I've just produced, which is there. And I divide the two. There we go. And as you can see, we've successfully got rid of all the low frequency rise, all the rubbish, and cleaned up the response. And the high frequencies, we've got sufficient absorption in the chamber to be able to measure reliably and cleanly. Once it's set up, away you go. And
can I ask, Geoff, if you were to do a similar measurement into a rectangular box, what differences would you see?
You get a horrendous response. In a rectangular box, you typically get a response which is going up and down by 15, 20, 25 dB or more, all over the place. The EQ.
So it should be like a cone filter effect starting at some, I don't know, mid-frequency, something like that, and then just having harmonic.
It's not so much that, it's not even often very regular. What I'm doing now is I'm just moving the EQ curve down so we can see it visually on the screen. And as it's coming into sight, you can see how clean and how straight and how smooth it is. Right, there we are. That's how little correction is required for this chamber. Now, the 350 is extremely good. The bigger chambers have a little bit more variation in them, but either way, it's not sufficient to be a problem. Modern instrumentation can take account of that all day, every day, without blinking an eyelid. And
just,
typically, the variation you'd normally get would often be from 30 dB there up to -10 or even up to 0 or back. Now, if you've got those sort of variations going on there, understanding what the hell's actually happening with the drive unit becomes impossible.
So is it the case that, say, for a rectangular box, you're getting huge peaks and dips?
Yes.
Yeah, and
yes.
that's quite a distinct thing from just having this constant bass lift.
Yes.
Yeah.
Exactly. So that's one of the advantages that the TTC gives, that we've got a stable response that is increasing, but probably it's a pressure response at low frequencies, which means that the data is reliable. We can see on the lower graph here, we're looking at the time thing. And if I zoom in on the time, we can see that the pressure there, we've got a long wavy response there, which is indicating the low frequency response, which we need to take out, which is the rising response on the SPL. And if you look at the data, the green data with the actual response there, you can see how quickly that settles down and behaves itself, so that we can reliably measure to very, very low frequencies as well, much lower than the typical anechoic chamber can measure. So one of the wonderful things about the TTC is that in many respects, it can actually do a better job than an anechoic.
And also you could actually echo the R&D tool on the production line, and that
absolutely,
because a lot, they just have a jig similar to that, but maybe they don't have the right measurement setup behind it. What's inside the box, so to speak, inside the tetrahedral.
An interesting curve is that here to my right, I've got a TTC 900. And that's the curve of the 900 versus the curve of the 350. And if I move them down, because they're measured at slightly different distances because the physical design, and overlay the things, we can see that we've got a slightly different response in the base area, as we would expect, because the 350 is a smaller chamber, and so it gives a bit more of a rise, circa about 100 hertz, and then the response falls off, whereas the 900, we actually get down lower in the response at the very lowest frequencies. But you could any loudspeaker engineer could take a look at the data sent from either of those two chambers and say, oh yeah, that's the same speaker. It's just been measured at a slightly larger distance. And so we've got a little bit more resolution at the high frequencies. We can see all those peaks all line up exactly. It's the same drive unit, and it was the same drive unit. In essence, that's what the TTC can bring to the party.
Okay.
So this tetrahedral shape, that's all about managing standing waves or reflections inside the machine?
Managing the standing waves, internal reflections. Inherently, you haven't got parallel surfaces. So you're discouraging the formation of the standing waves, and you're discouraging the problems getting started in the first place. And it's generally easier to solve a problem if it's not got going than it is to try and solve a problem when it has got going. If you're driving a car and steering, and well, we prefer to drive a car with the steering which has got nice and tight steering that steers in the right line, rather than one that's wobbling all over the place. It's just easier.
And so that's those spikes got 9K and then something, I don't know, it might be 15 or whatever.
That's in the breakup region of the drive unit.
That's actually the driver. That's not the chamber either.
No, that's the driver. That's the driver. That's the driver. That's the true response of the loudspeaker driver. It's slightly different at the higher frequencies there, because the 350 is measuring at a distance of 10 centimeters, whereas the 900 is measuring at about 316 millimeters. So we've got around about a 10, depending on how you calculate it, 20 dB difference in the levels. And of course, the wavelengths at those sort of frequencies mean that you're going to get significant differences in the waveform being produced at those different distances.
So a lot of manufacturers are when they're doing QC on a driver, they're also using a box. Are they using a box? Are they, or
exactly? Far too many of them are just using a box, and then they're wondering why they're not getting a good and a valid response out of it.
My question is, if you're using a box, you would be seeing spikes like you see at 9K, 15K, whatever the number is, elsewhere across the frequency spectrum. You'd have no way to know if that's the driver or the box. Is that right? Exactly.
You've got no way of knowing which is which. And because everything is all convolved together, you can't separate it out. You don't know whether it's the driver, whether it's the box. It's all happening literally at the same time. You can't even window it out effectively, because the whole thing's happening within half a millisecond of it all. So you've got no way of taking it back out. The only way you can take it back out is by designing it out. Which is what I've tried to do, to say, right, this is a design that doesn't have those problems, period.
Okay.
And then let's take the example. If you were to take that driver and measure it in an anechoic room, would you be seeing a curve more or less like that?
Oh, yes. I've done this many, many, many times, and you get a response like that. Often not as good. Often if you're using an anechoic chamber and a baffle, you will get discrepancies because the sound bounces off the end of the baffle and causes more problems from that. I
was curious about one thing. Mind if I ask these? You've got these IEC baffles that are used, and you place a speaker sort of off center on that.
Yep.
Does that end up meaning that regardless of what speaker you measure, you always see the same low frequency roll off because that's just the dimension of that baffle?
Yes and no. You always get a consistent response off of it because of the size of the baffle. And the size of the baffle means that you've got interference both the sound being reflected and refracted. Reflected where it comes to an edge and the sound comes back, and refraction where the sound goes past an edge and then it's suddenly unsupported, both of which will reflect back to a microphone and cause interference. the whole idea of the TTC is, because of the design of it, is that we haven't got, and if you still, if you look over to my, can you still see my camera?
Yeah.
Yeah.
Okay.
Yeah.
Yeah. And you can see my finger there. Yeah.
Mm-hmm.
And you've got a distance to the baffle of perhaps an inch, whereas up there you've got 3 or 4 inches. So you haven't got a constant anywhere. So you're just not going to get the same interference from the edge of the baffle that's going to cause interferences. Whereas the IEC baffle is inevitably just a square or rectangular panel. Causes consistent problems. So I've taken account of a lot of things within this design. Those are just 2 of them.
And so there's a measurement microphone mounted inside that chamber, and put the speaker and measure that. Is the position of that microphone quite critical?
It's not critical per se, but if I take that out, can you see that?
Yeah, I'll zoom in on it. Hold on. Okay. Yeah, sure.
Yeah, you take that out there. I've got a jig there, and we can just place that on there. And now we set the microphone distance using our jig.
Okay.
And we know exactly where the microphone has been set. And so you can use a jig like that, and you can guarantee to set up your chamber the same every time.
Yep. And so that microphone position is kind of like a sweet spot where there's no nodes or antinodes.
Yeah. It's designed so that we get the best overall response at very low frequencies, as you could see from the EQ curve. It's extremely stable anyway, and so we haven't got any particular sweet spot that we need to watch out for. There's a little bit at the higher frequencies there, but even that's only, in this case, 5 dB or so, which is almost negligible.
So do your customers ask you if that chamber can do the standard 1 watt, 1 meter IEC baffle SPL sensitivity, and can it?
Oh, yes, of course it can. What you need to do, though, is you just need to get a sound calibrator. I've got one in here somewhere. But whatever, you're familiar with them. You put that on the end of your microphone and calibrate the level on there, and then you just take account of the fact that the microphone, instead of being at 1 meter, is now at 10 centimeters. And so we've got an offset on the sensitivity that we're measuring at. And we put that into the equation.
Yep.
Job done.
So you can just take the 1 kilohertz SPL from that box, and you just offset it, scale it by whatever scale factor, and you're getting the same.
Exactly.
Yeah.
Exactly. And away you go. And that's what I do. This piece of software I'm using here tends to normalize everything to 0 dB. But I'm using it because it's a very simple piece of software and doesn't obscure the details too much.
You're interested in curve shape for the most part in this case.
Exactly. At the moment, for you guys, I want to keep it as simple and clean as possible, with as least confusing bits and pieces in there as I can.
And how about deriving field small parameters? Is it useful for that? Because a lot of people just use, on a table, put a weight on and take those different impedances.
You could do that using a chamber. Another way of doing it. Sorry, if I get up for a moment.
Yep.
is that I've got a, just bring this round. So I'm going to cut this apart. I've got a acoustic chamber here, which is designed to go onto the back of a speaker. So it gives us a defined volume, and also will then restrict and stop external noise coming in to the speaker and affecting the measurement there. You could use that on the back of a speaker to define the extra volume, and you can use that to calculate the field small parameters.
So in that one, you take one impedance curve with it loaded in the chamber, no back, and another one with the back on?
Exactly. There's two methods. One is added mass, and the other one is added volume. Either of which can work, and have been proven to work for many, many years. And you could use this to do the same technique. Put that onto the chamber there, and then yes, you could use that to work out your field small parameters and all the main electro acoustic parameters. You can't get to the large signal parameters because they require measurement of the displacement, etc.
Right.
But the main parameters, yes.
All right. So commercially, let's if people are interested, hillacoustics.com is how they get a hold of you. Is there any reference products in the or reference factories or any kind of customers that you're allowed to mention that people might know? Is it top secret stuff?
Well, there's a lot of companies who've purchased from us. Little ones like Apple. They bought a few. We've got Jabil, many others.
So these can be used to micro speakers as well, like mobile phones,
yes.
And I can imagine the benefit, especially with the consistency and that kind of volume production is critical. And those guys are obsessed with measurement and QC control. So,
well, one of the things that the TTC 350, which is the small one there, is capable of doing is measuring at 10 centimeters. And the micro speaker standard, which has just come out, 63034, references measurements which are made on the mini baffle derived from the IEC baffle, which is about 1 meter by about 800 millimeters, so considerably smaller than the IEC baffle. But that's only measuring at 10 centimeters, which this chamber can do directly. And the problem with measurements like that is that the microspeaker is open at both sides and can be interfered with both sides, which make the measurements very variable from external noise, whereas the 350 can take account of that. And the stability of the measurements on these are far, far tighter. The 63034 references measurements which expand out to 1.5 dB at the very lowest end, whereas typically a TTC will measure consistently to within plus or minus 0.25 of a dB, which is the order of accuracy that most electronics is measured to, yet alone loudspeakers. Loudspeakers, it's unheard of to be able to measure to plus or minus 0.25 of a dB consistent.
I've got a in-ear monitor project recently, and they insisted on plus or minus 1.5, or they wouldn't take it. and that actually in some of the headphone speakers is a challenge to get in production executed. So,
well, the TTC will do that consistently. It's not a one-off. Okay, now can you see now? This is data on 100 drive units, which were measured over the course of day.
It's 100 different speakers, or that's the same speaker?
100 measurements of the same speaker.
Okay.
Measured over the course of a day. And as we can see, we're starting at just over 20 hertz, 25 hertz, going up to about 18K.
Looks like the maximum maybe 3 speakers, mate. It looks like the maximum there's 3.
No, that's the minimum curve, the average curve, and the maximum curve, and it is the data from 100 measurements. I can share the raw data with you, but because this is not a one-off. I've done this sort of thing dozens and dozens and dozens of times.
Yeah.
Right. And the expanded uncertainty from the minimum, average, and maximum calculate the standard deviation at each individual frequency, and then sum those back to third octave data, which is what I presented down here. As you can see, most of the biggest cause of variation, there's one little glitch there at about 250, but apart from that, most of the variation is at 30, 40, 50 hertz, i.e. around about drive unit resonance, which is where you would expect you're going to get some variation in a measurement, certainly over the course of a day. You wouldn't expect to get exactly the same measurement. And if you do get exactly the same measurement, something's lying to you. But the total variation even then is 0.15 of a dB, fractionally over. That's how stable measurements in the TTC can be.
Yeah, that's crazy. Your 30 to 40 hertz, this is just somebody bumped the table one time.
No, it's the drive unit resonance.
Okay.
And obviously, when you're measuring a speaker at resonance, the whole thing is flopping around, and you're not going to get exactly the same measurement every time. It's impossible. You never will. But this is what it's showing. Look, no, we're getting a variation in there, but we're getting exactly the variation that theory would say that we should get. Not we're getting plus or minus 3 dB, 5 dB, 10 dB, or whatever. No, we're getting a believable variation. We're not getting exactly the same data. I'm not covering anything up. This is what's and all.
All right, let's wrap this up for the day then. So, I think I said a few minutes ago, hillacoustics.com is how people can reach you. And
our sales go through spectral measurement, and the way to contact that, it's spectral measurement / chambers.
Anything else you want to know, Simon?
I think we might have covered enough for today.
No, but I think it's there's an obvious utility for this that I could see, and it echoes a lot of what I hear in development versus factory measurement. No matter if it's a speaker or if it's a circuit board or even a software development tool or a measurement software, whatever it is. They always want at the brand developments in Europe or US, they want their factory to have the identical tools. And the concept of having an anechoic in Boston, let's say, that is one size, and then their factory in Kunshan or somewhere near Shanghai, they have a different size anechoic, and then of course there's something else on the production line. it throws variables into it. So I know that this is just a test and measurement kind of theme that people want consistency across all the tools. So,
well, the TTC is designed to address that, and there's a range of different TTCs from the 350 over the small one through 900s. We've got a larger chamber of the 1500 currently in use in India. And all of them, once they're set up, will give comparable data between them. So, the R&D department could have, the big boy of the lot, but you could have potentially dozens of the small ones on the end of the production line where they're not, they're all there. All you got to do is just change over the baffle when you change over a drive unit. Well, you're doing that anyway, almost certainly. And then you've got consistency potentially right throughout your design and measurement chain.
Perfect. All right. Well, let's say goodbye to everybody. So thank you, Geoff, for joining us today. We really appreciate that information. I found it quite interesting. And thanks, Simon, for joining, and everybody watching. We'll put the links in the description below for the contact information. Go ahead, Geoff.
I was going to say, if I could give a quick plug for my book, Loudspeaker Modeling and Design. Anyone who's interested in more of the theory behind the chamber can look in there. There's an early white paper and some theory in there, along with further information on designing loudspeakers and systems.
Okay. And I think that the link to buy that's on your website, if I'm not mistaken, so we can put that in the description as well.
It's not, but you Google it and you'll find it anywhere.
We'll figure it
I'll have to sort that out, actually.
Okay. All right. So please like, subscribe, and share this, everybody. So have a great day.
Thanks,
okay.
Geoff.
Thank you very much. Cheers, guys.
Bye.